If you are choosing a vector database for a RAG app, here is a simple checklist and a tiny interface that keeps your code portable. Most pipelines break at retrieval.
You end up with noisy results or brittle integrations.
By the end of this video, you will understand the core trade-offs and have a tiny, portable pattern you can reuse across projects. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Vector search solves a practical problem. You have documents in plain text and a question in natural language. The goal is to find the most relevant passages quickly, so a language model can answer correctly. Success looks like concise, correct context returned in low latency and without weird, irrelevant hits. At a high level, a vector database stores numeric summaries of text, called embeddings. You query with an embedding for your question. Matching uses distance or similarity instead of exact words. That makes retrieval robust to wording and useful for paraphrase-heavy tasks. But it also shifts how you measure relevance. We will build a tiny toy pipeline. It creates a few documents, turns them into vectors with a small embedder, and runs a few flavors of queries. Each step shows a design choice you will meet in production. Now we start with the core data setup. This snippet creates toy docs, a tiny embedder, and stores vectors with metadata. It begins by listing simple documents and their metadata tags, so every item has an ID, a short text, and a topic tag. Next, it calls the embedder to convert each text into a numeric vector, and then writes those vectors into an index, along with the ID and the tag. The main idea is to separate content from metadata, so you can filter later. If you swapped the embedder for a different one, the stored vectors change, but the rest of the code stays the same. This setup gives you a stable shape to build retrieval experiments. Now, we run a straightforward similarity query. This example runs a cosine similarity query to get the best matching document. It computes an embedding for the incoming question, then compares that query vector to every stored vector using cosine similarity, which measures angular closeness between two vectors. The snippet sorts results by highest similarity and returns the top match and its metadata, so you can see which document will be fed into the LLM. The key takeaway is that this flow exposes raw similarity scores and a ranked list. If scores are low across the board, you either need better embeddings or broader candidate retrieval before ranking. Next, we restrict results by topic. This code filters by tag equal energy before ranking to enforce scoped retrieval. It first narrows the candidate set to only those documents whose tag is energy, then computes similarity inside that smaller pool. That pattern is useful when your app has multiple domains and you want higher precision for a specific domain. The cost is obvious. If the correct answer lives outside the tag, you will miss it.
Practically, you choose scoped retrieval when an upstream signal reliably indicates the domain,
and otherwise fall back to an unscoped search. Next, we combine vector and keyword signals. This snippet fuses vector and keyword signals with a tunable alpha parameter. It computes a vector score and a simple keyword score for each candidate, then mixes them with a weight called alpha that ranges from 0 to 1. Alpha near 1 favors the vector signal and will return paraphrase matches even when keywords differ. Alpha near 0 favors exact keyword overlap and pulls back on semantic matches. Tuning alpha changes precision and recall trade-offs. Use it when vector similarity alone produces semantically plausible but factually off hits, or when keyword matches alone are too brittle. Finally, we show the portability benefit. This snippet shows two interchangeable backends sharing the same query shape. The code defines a single query function that accepts a query embedding, optional filters, and the Fusion Alpha. Under the hood, that function can call a local in-memory index or a remote database. Both backends return the same structured results, so the rest of your pipeline is unchanged. This makes experiments and deployments cleaner because you can swap the index implementation without rewriting retrieval logic or prompt assembly. Mapping this toy flow to a real system is straightforward. Replace the tiny embedder with a production model. Move the in-memory store to an ANN index for scale, and add timing and logging. The code structure stays identical, and that portability is what saves time in the long run. Recap. Vector retrieval stores embeddings and metadata and ranks by similarity. Use scoped filters when you trust domain signals. One caveat: semantic matches can be plausible but incorrect, so combine signals or add verification. Next step: tune the Fusion Alpha across a validation set, or replace the similarity engine with an ANN index and measure latency and accuracy trade-offs. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.